So I've asked all speakers to stay in time because it's a parallel session so that people have the chance to change between the two lecture halls. I will show them slides, 5 minutes, 1 minute, and stop. Then we have maybe 1 or 2 minutes for questions. The first speaker is David Andriot from Munich, and the title of his talk is Non-Geometric Fluxes in Higher Dimensions 1.
Thanks a lot. So let me first thank the organizers for giving me this opportunity to present this work. This work has been done in Munich with my collaborators and has been presented in these papers and some work in progress. It's also in relation to many recent papers that I don't have time to talk about, unfortunately, but yeah, I'm really happy that there's such an activity recently on this topic. All right, so what is the topic? The topic is non-geometry. More precisely here, non-geometry in 4-dimensional and 10-dimensional supergravity. To be precise, I'm actually going to restrict myself to the SNS sector, the bosonic fields being obviously the metric, the B field, and the dileton. So what is non-geometry? Well, it's a long story. I don't have much time. Let me give a brief overview. So let me first say that it's described very differently in 4D and 10D. So in 4D, non-geometry appears via some specific terms which occur in the potential of supergravity. These terms are generated by some specific integers, Q and R, which have a very specific set of indices here. They are called the non-geometric fluxes. They can be related to some specific gaugings in 4-dimensional gauge supergravity. These terms are actually good for phenomenology, and that's the reason for me to talk of this topic in this conference. They can be used or have been used to stabilize moduli for Minkowski solutions, or also to find de Sitter solutions. So I think that's the motivation for the topic. We'd like to understand all this topic better to be able to use these nice properties, basically. So that's for 4D. For 10D, the story is different. Actually, non-geometry originally came in 10D in these papers in 2002. I don't have much time to talk about it. Dieter already talked about it yesterday. Let me say two things. First, the relation to 4D is pretty unclear. And secondly, as Dieter said, if you take a 10-dimensional configuration of fields, which is non-geometric, typically they actually look ill-defined, meaning they're not single-valued and there are some global issues. So that's all we need to know here in this talk about 10D non-geometry, but there are global issues, basically. All right, so given this setup, 4D, 10D, there are natural questions to be asked. First question is, since these 4-dimensional non-geometric terms are interesting for phenomenology, can we obtain them from a compactification, say? The answer is no, or no until recently, maybe. And the reason is that these terms have a very specific shape, a very specific dependence on scalars, and this dependence cannot be reproduced by standard supergravity ingredients. Another way to phrase the question is, what is this Q and this R? Is there a 10-dimensional meaning or origin for these two objects? As I've said, this Q and this R have a very specific set of indices, and naively you don't find any fields in 10 dimensions which has this type of indices. So it's not clear what they could come from in 10 dimensions. Okay. One could maybe think that relating this to 10-dimensional non-geometry would help. For instance, obtain that from a compactification, but this is also difficult. As I said, the 10-dimensional non-geometric configuration of fields, say, is usually globally ill-defined. So you cannot integrate over it. You cannot perform the standard compactification procedure because you don't know how to treat the global aspects. Okay, so yeah, this is the situation. And in this talk, I want to present you some progress in relating the 4D and 10D point of view, and also answering these questions, basically. Okay, so the answer we found comes from a field redefinition. So the idea is that you take your NS fields and you redefine fields, so you rewrite things a bit. If you do that, the Q and the R will appear in the 10-dimensional Lagrangian. So this means that this answers this question, that the Q and the R fluxes are not exotic objects. We don't know where they come from. They are actually present already from the start in the NS Lagrangian. And it's just a matter of rewriting things to see them appear, basically. So this gives an answer to this question. And we actually got answers to the other questions because, or at least in some examples, the new fields you get after redefining them turn out to be globally defined. So you don't have any global issues anymore once you look at the new fields. Therefore, you can perform the compactification. And if you do that, you obtain the good scalar potential, meaning you obtain the good non-geometric terms in the potential. So this also provides an origin to this term. All right, so the plan of my talk is to detail all this. First, the field redefinition, and secondly, the dimensional reduction. Okay, so the field redefinition goes as follows. So the key object is beta. Beta is an antisymmetric bivector. So in particular, it has two indices up. So the reason for considering this comes from some literature using Dry's complex geometry applied to supergravity. In these papers, there were some arguments saying that whenever you have some non-geometry, beta could be appear, basically, or could appear, and it would be good to characterize the non-geometry. So there should be some relation between these two things. There were also some formulas proposed to relate the beta to the non-geometric fluxes. So I don't have time to review these arguments, but we were inspired by these ideas, basically. And so the idea is, okay, let's make beta appear, and this should be good for non-geometry. So how do you make beta appear? Well, we understood that beta can appear if you reparameterize the generalized metric. So you probably know this matrix, the generalized metric, which depends on the metric and the B fields. You can actually reparameterize it this way in terms of a new metric, G tilde, and this beta here. If you do that, well, you get some equality, so you get some relations between GB and G tilde and beta. These relations can actually be repackaged that way, which is very convenient, and Peter in the next talk will be using this relation. So in addition to these equalities, we also wanted a new dilaton. So we actually introduced a phi tilde that we defined that way in order to preserve the measure. So the bottom line is that we have a field redefinition between the NS fields and these new fields, the new metric, the beta, and the new dilaton. And according to this literature, beta should be favored for non-geometry. All right, so let's do the naive thing. Now I just take the NS Lagrangian, and I just apply this field redefinition, and let's see what happens. Since beta could be related to the non-geometric fluxes, it could be that they appear in the Lagrangian. And actually, this is what happens. Yes?
Sorry, what you call field redefinition also includes T-derivative transformations?
No, it's for me, personally, it's a different thing. It's not a T-duality. So I take this NS Lagrangian and I do the brute force replacement and redefine my fields there. The computation is quite involved. So in the first paper, we made some assumption to simplify the computations. Even if you do that, the computation is still a bit involved. So the Ricci scalar can be expressed in terms of a new Ricci scalar plus all these terms here. However, if you also do the replacement for the dilaton and the H flux, it turns out that there are impressive constellations, and all these terms simply drop out. And you are left with a simple expression, which is this. So you get indeed the new Ricci, the new dilaton, and some Q squared. So we call that L tilde and a total derivative here. So the Q is here given by the derivative of beta, and the square is the standard square with contractions. Now in the next papers, we actually dropped the assumption, and so we got more terms here which go together with the Q, and also an r squared here. So this we actually called r flux, and the square is also the standard square. Again, there are two ways of doing the computation. The brute force methods, which actually can be worked out. It's a bit lengthy, but it's doable. Another method is to use double field theory, which eases a lot the computation, and Peter is going to talk about this. Okay, so the bottom line here is that if I do this field redefinition, I get some objects Q and R which appear in 10D. Are these really the same things as the four-dimensional Q and R that I talked about? So I'm going to do a dimensional reduction and obtain the non-geometric terms in 4D to show you that it's indeed the same. Okay, so I go quicker here. So I'm going to do a rather simple dimensional reduction where I only consider two scalars, the volume and the dilaton. I start from 10D theory and I get a 4D theory basically with a potential depending on this rho and dilaton. So I don't detail this, it's rather standard. So for instance, if I take the NS-NS Lagrangian, I obtain two terms in my potential. The first term is due to the H flux, the H square. The second term is due to the curvature, so the Ricci scalar. What about non-geometric terms? So non-geometric terms are actually argued to enter the potential in that manner. So you add two new terms, one due to the Q flux and one due to the R flux. As I said previously, you cannot mix this term with the others because they definitely have a different dependence on the moduli. So you cannot obtain them with the standard tools of supergravity. So the result we get is that if you take the L tilde, so the new Lagrangian, instead of the NS-NS, you do get the good potential in the sense that you reproduce these terms here. So more precisely, here's what we get. We get a new term with the Ricci, so the curvature, a term for the R flux, given by what we call the R flux, and a term for the Q flux, also given by this Q square and other terms here. So the bottom line is that if I take this L tilde and these 10-dimensional objects I call Q and R, they do give the good potential. They do give an origin to these two terms that I was not able to get before, basically. Now, I agree with you that this expression is a bit complicated. So the precise matching to the four-dimensional Q object might need to be improved. For instance, if we could get a square here instead of this whole thing, that would be better. But in any case, I obtained the good term in the scalar potential. The double field theory will bring a nice interpretation for this term, so I refer you to the next talk as well about it.
Excuse me?
Yeah.
Is this always on the same duality orbit as a geometric compactification?
No, it depends. It doesn't have to be. So, yeah, this leads me to this last slide, actually. I haven't talked about global aspects yet. So I've just done the dimensional reduction assuming things were globally defined. But it actually depends whether things are globally defined or not. So I've told you that I can always rewrite the Lagrangian and NS-NS Lagrangian like that. However, if I start with a non-geometric configuration in 10D, this Lagrangian by definition will be ill-defined. I cannot integrate it because there are global issues. So I cannot perform my dimensional reduction on it. I cannot get the terms. However, it happens that for some examples, when this is ill-defined, this is actually well-defined. So how can this be true? Well, it means that all the problems I had here can actually go only into the total derivative. So in that case, what we propose is actually to forget about the total derivative and just consider this L tilde, and this is then the good low-energy description for string theory on a non-geometric background. That's what we prescribe. If you do that, of course, as I said, you can take this L tilde, integrate it, and you get the good non-geometric terms in the potential. All right, so this establishes basically a relation between 4D and 10D non-geometry, because if I start from a 10-dimensional non-geometric configuration, I can go through all these steps, and I get in the end non-geometric terms in the potential. So now there's a relation between the two. All right, since I'm out of time, let me just flash the conclusions and outlook. What I want to stress is that here we've done an SNS. We'd like to extend that to Ramon-Ramon or other sectors of supergravity. And after that, I hope that this would give us access to new backgrounds, new interesting backgrounds to be used for phenomenology. Thanks.
Time for questions? At the very end.
But can you also do this with the H-flux in the background so that you have all the possible terms in the scalar potential?
Not yet, because the field redefinition we have totally gets rid of the B field. You get a beta instead. So if you want to have the H-flux at the same time, you would need both a B and a beta, which is actually too many degrees of freedom. So either you have B and beta along different directions, and then H and the non-geometric fluxes along different directions, for instance. Or you could imagine something more involved with some constraint to be added or something like that.
But then this means you're probably on the same duality orbit as a geometric compactification, no?
Not always, because of this, because this field redefinition is not a T-duality for me. So to me it is decoupled. So it could be that I have a globally well-defined solution with G and beta, which cannot be related by T-duality to anything. But still, it would be an interesting solution.
Okay, so last question?
It's related to the same thing, but then you're changing physics by applying field redefinition?
Yeah, so in particular in the case when it's not T-dual to any nice geometric solution, yes, you get new physics, exactly.
Okay. Very last question.
So you say that given beta, you can get some non-trivial Q and R fluxes. Do you think you can generate arbitrary Q and R fluxes that satisfy the Bianchi by some beta, or is there some further constraint on these fluxes?
So the Bianchi are not automatic given the formulas for Q and R. Yeah, I think it brings in additional constraints. Yeah.
But even if you satisfy those ones, do you think, because Q and R of course are generated by the same field, by beta.
Yes.
So that must yield yet additional constraints, I would think, that are not coming from the Bianchi. I would think, maybe, but.
Why? Why would there be additional constraints?
Well, because you don't have enough degrees of freedom, I suppose, to generate more general Q and Rs. It's contrasted to the gauge and geometric fluxes, where you've got two fields, both the two form and the metric generating gauge and geometric fluxes. Here's just a single field.
When you look at the formulas for Q and R, they're actually independent quantities because.
You still have G tilde, so to say, the dual.
But that's not appearing in these definitions over there, right? No, I think indeed G tilde should play
But
a
you have
role.
also the term, the potential, which is called R tilde, which is there.
So for instance, here you've got the beta, which is contracted on the derivative, which is a very specific contraction, which can actually take that to zero. So I think these two quantities are actually independent. But yeah.
Okay, so we thank you.